Hello again everybody, welcome back to another example video. In this video we are going to determine if a given matrix is orthogonal. I think the last video I did a linear proof on checking whether a matrix or why an orthogonal matrix contains an orthonormal set of bases in the column vectors. So if you want to check that out, it should be in the top right corner. But other than that, we are going to go ahead and get started with the examples. So what it means to be orthogonal, or for a matrix specifically, is for a matrix to be orthogonal, that means its transpose is equal to the inverse. And so that's all we're going to be pretty much doing. We're going to be taking the transpose of the matrix, and then we're also going to find its inverse. And if they're equal to each other, then that means they are orthogonal. If they're not, then they're not orthogonal. So the first example is a 2 by 2 matrix. So the transpose, as always, those are the easiest ones to do. We just switch, in this case, it would just switch to two elements. And so the main diagonal, as always, stays the same. And then this would be root 2 over 2. And the everything else just flips. So this bottom left would be root 2 over 2, and then the top right will be negative root 2 over 2. And so the inverse, now for the inverse for a 2 by 2 matrix, that one's easy to calculate. So the inverse, we will see that this will be equal to 1 over pretty much the determinant. So this would be root 2 over 2 times root 2 over 2, and so that would be 1/2 plus 1/2, and so that should be 1. So we have 1 over 1, and then the matrix, remember, we flip the main diagonals, or we exchange places, which nothing new happens, and then we multiply everything else by a -1. So this would become negative root 2 over 2, and this would be root 2 over 2. And so because this is multiplied by 1, this, our inverse matrix, P, I guess our inverse matrix will just pretty much be the same thing. It would just remain unchanged. Root 2 over 2, root 2 over 2, and then this would be negative root 2 over 2, and then it's just root 2 over 2. And we can see that this is the same thing as the transpose. And since they're equal to each other, then yes, this matrix is orthogonal. So yeah, orthogonal. Orthogonal. Cool. So now let's move on to the next example. So next example, this time we have a 3 by 3 matrix. So a little bit more work, but let's just go ahead and knock out the easy part, the transpose. So the transpose for this matrix, this will be, as always, the main diagonals remain unchanged, 1 and 4/5, and then everything else just kind of flips. So we have 0 and 0, so this remains the same, and then the 3/5 also remain the same, since they're both 3/5, and then 0, 0, that remains the same. So cool, the transpose is the same as the regular matrix. So now to find the inverse. So to find the inverse, you remember that we have to pretty much make a big augmented matrix. So the first part, or the left side of the matrix, or the augmented side, is the original matrix. And then the right side of the augmented matrix, it's its corresponding identity, which in this case is a 3 by 3, so that's supposed to be 0. So here we go. And so now we have to create the identity matrix on the left side, and then on the right side it's our inverse. So the first thing that we are going to do is we can all put this in. Okay, so we want to cancel out this, so we kind of multiply by a common, or make this into like a common factor? No, denominator. No, I forgot what it's called. Point is, the first row we are going to multiply by 3, second row we're going to multiply by 4, so what we end up getting, this will be negative 12 fifths, 0, 9 fifths, and then the second row remains unchanged. This will become 12 fifths, 0, 16 fifths. And so we multiply this side by 3, this one remains unchanged, and then the other side by 4. Alright. So now what do we do? So now we can cancel out this and this. So we're just gonna add them together, or we're gonna add the first row with the third row. So this will cancel out, so it'll be 0, it'll be 0. Then we have 9 plus 16, which is 25, divided by 5, it should become 5. Second row remains unchanged. Third row remains unchanged. And because we added, this will just be 3, 0, 4, then 0, 1, 0, then 0, 0, 4. Alright, so what we can do now is multiply the bottom part by 5. So we're going to multiply this part by 5 so we can get the 12 and the 16. And then we are going to flip it to make it go to the top row. So that way this 5 here, which ultimately is going to be a 1, it's going to be at the bottom right, which is where we want it to be. And again, the second row will remain unchanged. So we multiply by 5 and then move it to the top. So this would be 12, 0, 16. This remains unchanged. And then 0, 0. And we can pretty much divide it by 5 already. So this will become a 1. And now this would be 0, 0, because we multiply by 5. This would be 20. Still remains unchanged. And then this will be, we divided by 5, so this would be 3 fifths, 0, and 4 fifths. So now what do we do? Well, we gotta get rid of the 12 and the 16. So what we're gonna do is now we're gonna divide the first row by 16. And this will leave us with 12 over 16, 0, 1, 0, 1, 0, 0, 0, 1. This would be 0 and 3 fifths. The entirety of the second row will remain unchanged. And then this will be 20 over 16. Alright. So now we are going to cancel out this one right here. So this will leave us with 12 over 16. We can reduce that, divided by 4. So this would be 3 fourths, be 0, 0, 0, 1, 0, 0, 0, 1. And then on the right side, this would be, because we subtracted, the negative 3 fifths, remain unchanged. The 20 over 16, that will be subtracting by 4 fifths, 80, so 5, 80, 16, 9 20ths. Second row as usual. And then our third row unchanged. And so cool, we're almost done. So all we have to do is multiply the first row by 4/3. And so what we end up getting is the identity matrix on the left side. And then on the right side, it will be, this will be 4/3. So the 3's will cancel out. So you have negative 4 fifths. And then 0, 3 fifths. Second row, unchanged. 4 fifths, 4 fifths. Should be 0. And so now you have to, again, we're multiplying it by 4/3. So 4/3 times 9/20. The 3 will remain, or the 3 will reduce the 9 to a 3. 4, 5 will be 5. So we will get 3/5 on this side, and this will be our inverse matrix. And if we move back up to the top, we can see that we have -4/5, 3/5, -4/5, 3/5. Second row is the same, second row is the same. 3/5, 4/5, 3/5, 4/5. They are the same. And so we can see that our inverse matrix is the same thing as our transpose. So that means this is also orthogonal. And that is pretty much it for this video. Thank you so much for watching, and I'll see you in what I believe is the last example.